All right, well, let me thank the organizers, Trygve and Stur, very, very much for putting together this wonderful meeting. And I was definitely not there at the beginning. And reflecting on the title that I gave in light of Kieran's talk, you may infer that I dropped physics as a first-year undergraduate, and I didn't understand pure math, and I got left with chemistry and applied math. Anyway, so let's see if this works. Can I? Yeah, okay, so let me maybe start by saying that without the community, I would, of course, not be here. So in other words, my first acknowledgement is to the community as a whole for building the framework, laying the foundations, providing the inspiration, sometimes the competition. It's absolutely vital. And then, of course, there are the specific individuals, the ones who I've collaborated with and the ones who I haven't collaborated with. But without John Popel, I would not have learned the model chemistry approach and sort of bleed it when I am cut. Without Peter Gill, I would not have worked on linear scaling, range separation, and I don't know what would have happened to QChem. I think I do know what would have happened, actually. Without Axel Becker, I couldn't have done the work on functionals that I will describe. It all builds on his foundation. Without Stefan Grimmer and Troy Van Voorhis, the dispersion corrections that are built into the functionals that I've developed would not be there. So anyway, you stand on the shoulders of others. And then as a professor, I grew up loving to code, and then I became a professor and had no time to code. So the group members who are able to work with me and adapt to my style as I adapt to theirs are really what makes it possible. So Chris White, Roy Baer, Christian Oxenfeld, Yihan Shao are the people who made the linear scaling work that I'll briefly discuss possible. So Hirata, Andreas Droy, and Jenny Weissman were my fellow adventurers in TDDFT. Jengda Chai was the postdoc who refused to work on anything else but functionals, and we adapted to each other. He wanted to do kinetic energy, and we compromised. And Nabe Marderosian was the second round, and that's basically what I'll talk a little bit about. Maybe just some perspective. So my doctoral studies were with John Popel and were thoroughly without DFT. I worked on 2 electron repulsion integrals inspired by Ibarra and Saika. I worked on direct SCF following Jan Almlöf, one of the giants in the development of fast electronic structure theory methods. And then with John and Krishnan, I worked on correlated theory, and that was all great. No course or seminar I ever attended mentioned DFT as far as I recall. I'm pretty sure I never had a discussion with John about it before I left Pittsburgh. And I think my training, I knew about Tom Ziegler and I knew that X-alpha existed. It was this mysterious method that because you couldn't understand it, you didn't think about it. But this was the pre-DFT norm. Sanibel in 1989 did have DFT, but Peter paid more attention than I did. I heard Axel's talk and then I forgot about it. My view changed then when I was a postdoc learning surface science with John Tully at what was then Bell Labs. I got exciting preprints from Pittsburgh and learned about Gaussian/DFT. And as years went on, there was palpable excitement that I felt and imbibed, hearing from Axel, Popel, Handy, Skazit, Gus, and Dennis, others at conferences. So this then moved on. And so I arrived at Berkeley as an assistant professor in August of '92 to work on excited state theory and hot electrons at surfaces, just another kind of excited state, and to some degree I did. But Gaussian 92 and its DFT extension were released soon afterwards, and as we've already heard, it was easy to use, robust, and quite efficient, and it landed in the hands of non-specialists and became widely used. That's what you all know about. And then, as many of you know, the release of Gaussian 92 was not exactly a peaceful event, to say the least. And in fact, on his Christmas vacation in December of 1992, Peter Gill, one of the key developers of Gaussian 92 DFT, began writing a new program. And his fellow group member, Benny Johnson, joined him almost straight after graduation. And John Popel, in fact, signed a 6 years, a long no-compete agreement in order to sell his Gaussian shares and disengage himself from Gaussian. So this was interesting, and a bit naively, I told Peter and Benny on the one hand, and Mike and Gaussian on the other hand, that I'd be happy to collaborate with them both. And this led me to becoming very quickly Gaussian free in '93, and in fact banned by Gaussian. And now working mostly with QChem, which at that stage was very much a nascent code, my research trajectory was perturbed. And so what is someone to do if they have lost their code, don't know anything about DFT, but do know something about trying to write efficient SCF code? Well, you begin thinking about the rate determining steps. So, well, one line change, I guess, echoes here. So computational bottlenecks was where I started working, and the Coulomb matrix is one such bottleneck, a very simple one and connected to 2 electron integrals. And it was again from Peter that I learned about Greengard and Rockland's fast multipole method for the interaction of point particles, gravitational interactions, for instance. Our basis function products are our particles, but they're not point particles. And a brilliant graduate student, Chris White, worked with me to generalize the FMM to continuous charge distributions to make the CFMM. And it's a tree structure, and it gives you linear scaling with controlled precision, and it works really, really well. And that takes care of distant interactions through intelligent collectivization. Then you also need to address the near-field Coulomb problem, and one might just do 2 electron integrals, but when you think about it, the J matrix is so simple. You can pre-process a density and post-process a J matrix with some of the recurrence relations of 2 electron integrals and save a great deal, factors of anywhere between 5 and 20, depending on the angular momentum. And this, again, is something that Jan Almlof was thinking about, and it's great for any sized molecule, and especially great for linear scaling. So here's some of our ancient results from 1996, showing linear scaling in graphitic sheets in the modest 321G basis set, but as Erin told us, the workstations in those days were a bit modest. I think this was a Sandpiper, a DEC Alpha. Anyway, Chris made amazing use of it, and you can see 2 things here. The first is, let's see, I'll do this with the mouse. The conventional quadratic scaling ERIs are greatly speeded up by the J engine, even with only those low angular momenta. And then the 25 pole, that is roughly 10 to the minus 10 accuracy CFMM, exhibits linear scaling in this 2D system. It exhibits linear scaling in 3D as well. Oops, I'm going the wrong way. And with controlled precision. So the difference between 10 poles and 25 poles is something like 4 or 5 significant, at least 4 significant figures. So the CFMM really worked. Then another thing that I thought about in those days was the problem of diagonalization. And the first story I told you was a success largely. This one is a much more nuanced story, and so it's useful to discuss as well. In principle, all we've got to do is find some representation of the Heaviside function to act on the Fock operator that we've just made in linear scaling effort, and we should then be able to make the density matrix. And as Walter Cohn taught us, the density matrix in real space decays exponentially with some decay length L as a function of the inter-electron distance. And in a little more detail, Roy Bayer and I worked out that it is, of course, inverse in the square root of the gap and proportional to the number of digits of precision you want. And this is a little bit nasty. And so this illustrates, this plot here illustrates on the x-axis the log of precision, and on the y-axis how many lineal neighbors you have. And of course you should then square it or cube it in 2D or 3D, and the point is that a large gap insulator in low precision is quite easy to achieve linear scaling, but a small gap semiconductor in high precision is then very, very difficult. And so essentially that's one thing that has held back linear scaling diagonalization. It is hard to get the crossover, and there is this sparsity challenge. And in fact, there's something else as well, which is diffuse function containing basis sets damage sparsity and in fact appear to violate the cone bound. In other words, variationally minimizing in a large basis set gives you non-sparse structure out to quite non-physical distances. So linear scaling replacements for diagonalization is something I then stopped working on because I got stuck. And I think this is an area that could still use a breakthrough. All right, I think I'll just skip through this, but maybe there's a theme here, which is something great about quantum chemistry, in my view, was expressed to me beautifully by the late Reinhard Ulrichs, who said that in weather forecasting, people get together at conferences and debate about, the grid density or how long you propagate in time. But in quantum chemistry meetings, we get together and tear down the foundations and rebuild them. So Gaussian basis functions might be replaced by numerical atomic orbitals, or four-center two-electron integrals may be displaced by semi-numerical integrals and are substantially displaced by resolution of the identity. So we live in a vital field, and I love it for that reason. Okay, now I want to talk about my transition into time-dependent DFT, because remember I started off trying to work on excited states, and I did that for a couple of years and did single excitation CI-based theory, linear response coupled cluster theory, and various approximations, but they were quite frustrating because I got terrible results for open shell systems in particular at the low-level CIS-based level of theory. And then there was this tempting theory from Runge and Gross originally, and then brought really into chemistry by Cassada and Ulrichs, with contributions by many others as well. And they reported promising results. So a very bright postdoc, So Hirata, arrived, and I asked him to turn QChem into a TD-DFT engine. And he did it extraordinarily quickly. Restricted and unrestricted orbitals alike. I suggested he could try the Tam-Dankoff approximation, which hadn't been explored, and he did that as well. And the quality of results was great. This was the nearest I came to sort of the Popel-like moment, I guess, in DFT, which is that I had been struggling away on excited states, and then suddenly what I used to think was difficult became quite easy. Even the LSDA worked remarkably well. And not just for single excitations, but for states that I thought had substantial double excitation character in a wave function picture. So evidently the orbitals are better. This is some data that I got together with So and my late friend and collaborator Tim Lee, and it just shows you how beautifully things work out for radical cations, the naphthalene radical cation. The TD-DFT accuracy is similar to CASP-PT2 and dramatically better than single excitation CI. And that's great. And that is BLIP, by the way, or BLIP. And if I'd shown you LSDA, it would be very, very similar. So we were in a period of high excitement around 1999 about this, and then it got even better. What are those extra states that CASP-PT2 didn't get? Well, that was an active space limitation. It was a pi active space that was used in the CASP-PT2, so it couldn't get sigma to pi star type excitations. So that was all good. And it wasn't an accident of just one molecule. Later, So and I did a boatload of molecules, and you got roughly a quarter of volt RMS error. So it was great. Well, a bit like John went off DFT a bit, my love affair with TD-DFT ran into trouble just about 3 or 4 years later when we were collaborating with an experimental group at Berkeley, looking at this complex that underwent electron transfer. And we got very, very extraordinary results. Namely, the charge transfer states came in ridiculously low, absurdly low. And then we stripped out the linker and we began stretching them, and we discovered that the Coulomb attraction was missing. The curves are dead flat. Those should be 1/r attractions, and they were dead flat. They should be above the Q states. They were way below, and so this is a disastrous manifestation of self-interaction error, and was my sort of rude introduction to it. We actually thought we had a bug in QChem. We looked quite hard for a bug. There must have been some cause why we were accidentally throwing away the long-range attraction, but eventually we realized that you got 20% of it back with B3 lip, and then 50% with half and half, and we put it together. So anyway, density functional development has to then address the failures that we understand exist, however we ran into them. And I'm just telling you my own experience. And so limitations of exchange, limitations of correlation, and Zheng Da and I began working in 2005 or so on an attempt to grapple with these, again, informed by what the community was doing. Without the community, we couldn't have done this. So we were aware from others like John Popel about H2+, about bad barrier heights, our own sobering TD-DFT experience, and range separation was available. Andreas Savin with the concept, Peter Gill with the short range LSDA, and contributions from others showing that this was really worth looking at. Axel with the B97 basis functional, and Stefan with the D2 correction. So these were things that we could put together. The only thing that seemed to be missing was some systematic optimization. Range separation, dispersion, the parameters all developed together, and at least a couple of exact constraints satisfied, uniform electron gas, and some data. So we gathered 412 data points. We even held back about 300 pieces of data, which was unorthodox for the time, and we wanted to just see how things transferred. And we trained some functionals that we never intended to use. So over here on the right is a trained GGA of the B97 form with the same number of exchange and correlation parameters as the hybrid B97 form, which we also retrained. And then we trained these three variants of range separation, one without short-range exact exchange, one with, and one with both short and long-range exact exchange and dispersion. And why is this one worse than that one despite having extra freedom? It's because I'm only showing you a subset of the data. This is training data. And then on the non-covalent interactions, we see clearly the value of the dispersion correction, even in its early generation. And then the test results were equally encouraging. We then tested against existing functionals, a standard GGA blip that we would use, or B3-lip, and we could see that for the held-back data, which had different elements than the elements that we trained on, and a set of largely independent weak interactions, things transferred well. And one of the design goals was reducing self-interaction errors. So this is the argon dimer cation, and it's just showing you that the range-separated hybrids do substantially better. They go flat. They don't go flat to the right number, but they don't turn over the way hybrids and GGAs do. And so we got a useful functional out of this, and so the project was in some sense a success. We were tempted to try to go further because we could see the success that Don Trular's group and others, also the early meta-GGA development by Axel and by John, but looking at the semi-empirical approach we were taking made me nervous, and we didn't want to fall into the land of blatant overfitting. So instead we went the double hybrid route, and then Zheng Da got a job and a wife and left for National Taiwan University, and lacking a good idea, I took a break from functional development and did other things. And then this paper hasn't yet been quoted here, but obviously it's an interesting one. Authors, including John, wrote that atomic densities became closer to the exact ones, reflecting theoretical advances until the early 2000s, when this trend was reversed by unconstrained functionals sacrificing physical rigor for the flexibility of empirical fitting. And this slightly odd data was presented. Data points are functionals, the x-axis is time, the y-axis is a measure of the deviation in the electron density of a bunch of spherical atoms, and the line is a guide to the eye to show you lowering error through about the year 2000, followed by increasing error then. And I looked at this appalled when I first saw it and tried to find out where our omega B97X functionals lay, and then was slightly consoled to discover that all 14 of the worst post-2000 functionals came from only one research group. And there's a small guide to the eye there. But the message was clear. We had to be careful about overfitting. And so then this very much was in sync with what we were actually already working on and already thinking about before that paper was published, which is that we needed to greatly expand the amount of data and try to use a greatly expanded amount of data to not greatly expand the number of parameters. And so we want to then search for the most accurate functional, and I put it in quotes because we have to define that is least empirical. We also have to define that. And we made, or when I say we, Nabe compiled, interacting with me, this large database of 5,000 data points. And we split it up in a way that actually is more conservative than typical machine learning. We hold back around 4/5 of the data to not use in any training. Instead, the primary test data is used to select a functional, and the secondary test data is then used to validate the selected functional, to test against selection bias. The weights are human activity, and they're a great challenge. Least empirical, well, I had in my mind's eye the idea of a hockey stick plot for predictions, where as you added parameters, the RMS would go down, and then you add more, and it would go back up again. And so that's basically how we decided to stop. The functionals, this owes everything to Axel, to Stefan, to Peter and Andreas for the ingredients, and they are basis functionals. The parameters are the linear coefficients. If you truncate 3 expansions at m equals 4 and don't apply any constraints, you've got 15 parameters. Each one could be included or excluded, so that's 2 to the 15th. You can just itemize them. You can fully search that GGA space, and that is what gave rise to omega B97 X-V. On the other hand, if we do the meta-GGA, this is where it gets a little scary because it's a 2D Taylor series. And so if we've got 5 times 5 times 3, we've got 2 to the 75th, and that's roughly Avogadro's number. So this is some sort of functional genome, and you had better tread cautiously there. And then range-separated exact exchange and VV10 non-local correlation, a van der Waal density functional from Troy van Voorhis, rounded out. And so we then did this search, and several trillion functionals were trained, and all but 4 were thrown away. The 4 that survived were then a rung 3 functional, 2 hybrids, and a double hybrid. And I can click through this, and you'll see nothing that surprises you. The interesting thing is then the search space, right? A 10 to the 40th search space, Avogadro's number to Avogadro's number squared in the case of the meta-GGA, and on the order of 100,000 for the GGA. The retained parameters, where does the hockey stick, your virtual hockey stick plot turn over? 12 of 144, or 10 of 16, or 12, or 14. Anyway, so basically, at least with the amount of data we have, the constraints we imposed, the degree of semi-empiricism was data controlled. And then the Jacob's ladder, how does it look? Well, these are 1 sigma errors, so multiply by 3 if you have high standards. And if I just look at, for instance, easy thermochemistry at 10 kcal per mole, 1 sigma error at the LDA, B97D3 is a functional we couldn't really beat by combinatorial training because it comes from a small functional space, so we didn't report anything at this level. But you can see for yourself the GGA improvement for easy thermochemistry or for barrier heights, factor of 2, and the dispersion correction giving you a factor of 4 for non-covalent interactions. The meta-GGA B97M-RV significantly improves easy thermochemistry, significantly improves barrier heights, and VV10 is very effective when it's trained with the functional to give accurate non-covalent interactions. If you go to hybrids, the best one is the meta-GGA, and you can see the easy thermochemistry improvement is modest compared to the meta-GGA. The barrier height improvement is significant, and then a double hybrid looking even better. Okay, so basically in a statistical sense, we, like others, agree with the idea that Jacob's ladder, if you include dispersion consistently, is a very, very meaningful concept in a statistical sense. Of course, if you draw a bad molecule and your sample size is 1, the LDA might be the best result and the double hybrid might be the worst. So you've got to think about things statistically, not ab initio or variationally. Okay, so I will wrap up here and hopefully leave some time for questions. So I was a slightly late witness to the rise of density functional theory in chemistry. The formal foundations are beautiful and the practical realizations are definitely useful. Maybe the most interesting story I told you is the development of omega B97M-V. That was successful. It's important to say that those trillions of functionals, there was not one best functional. There were tens of thousands of essentially identical ones. So we picked a representative of the most transferable. It was in no sense a uniquely good functional. The project was only a big success because no one else had done anything like it before. It may be possible, though it is definitely not easy, to make significant further improvements, and this is a project we are working with, and others are too. Undoubtedly, more diverse data is needed. Careful consideration about additional constraints is needed. Local hybrids are a promising additional descriptor, a more flexible descriptor. New machine learning tools are also valuable. And then I think it's really noteworthy to highlight Axel's breakthrough in double hybrids. There is really exciting progress at rung 5 right now. But I believe more robust alternatives to PT2 are essential if rung 5 is to realize its promise. And so one project I'm very excited about is regularized second-order Brillouin-Wigner theory, which is an MP2 scaling replacement in its generalizations. And then the other thing we're working on in the rung 5 spirit is new higher precision linear scaling algorithms, aiming for roughly 100 times more accuracy than is common with DLP&O. And a takeaway, or just a comment, strong correlation is a critical problem. And the best we can do to manage it, I think, is to always do stability analysis in DFT. In our data pruning, we subject every data point to stability analysis, and we will remove it if there is any doubt about the reference. And I'm not good at predicting the future, definitely not US election outcomes. I'm actually honestly not sure what will be the genuinely next big things in density functional theory, but I know what I'm working on, and I'm very excited to see what the community brings. So anyway, thank you for the invitation, and I'll stop there.
Yeah, we have ample time for discussions, comments.
So Martin, I'm sure you've seen the paper by Thomas Weymouth and Marcus Reier some years ago, where they pointed out the limitation of static DFT benchmarks. So basically, the jig of that paper was that if you just remove the strongest outlier, you can change rankings quite a lot. So what's your take on how does this affect training DFT functionals?
We actually had significant success with outlier detection and removal in the development of omega B97M parenthesis 2, the double hybrid. And so largely, I think one does need to be careful about detecting outliers and making sure that they don't unduly influence your function. So I largely agree with that.
Can I cite two famous people? Eugene Wigner, you know about? Apparently in his time, he had friends who were doing big calculations on big computers on some problem that interested him. And he had been told by them that they had gotten very far. And but he didn't get an explanation of the results. And he said, "Look, I'm very glad that your computer understands this problem, but I'd like to understand it too." But the other citation I'd like to bring to your attention is, I think it was claimed to be Fritz Schaefer, who said, "We'd like to get the right answer for the right reason." So how do you, if you look at this, to the fantastic picture that you've drawn for us, can you see how far we've gone in the direction of Wigner and And Fritz Schaefer as well.
Okay, that's a great provocation to respond to. Yes,
Well met.
So my guilty hobby, or what I used to call my guilty hobby, is energy decomposition analysis, which is the idea that if you have done a DFT calculation and you get an answer for the water dimer, the answer is 19.5 kilojoules per mole. Vaguely like the Hitchhiker's Guide to the Galaxy and the Meaning of Life, which is 42. And so revealing the physical driving forces for both non-bonded and bonded interactions is a relatively small part of our field, but one that is important and one that I enjoy, despite some controversy. And this is a very friendly field compared to that one. And then about the right answer for the right reason, I think one of the comforting things about John's Jacob's ladder is that as you add additional physically based descriptors, you can see the statistical accuracy of functionals improve. So I think we can say that we narrow the error distribution for reasons that are justifiable. The double hybrids bear a little bit of caution because they are built on a slightly more brittle foundation, PT2, which is well known to fail and is simply far less robust than some of the components, the other components. So I think there is room for improved robustness at rung 5, but broadly speaking, I feel content, I guess, about the physical content of the more accurate density functions. It's certainly hard for me to tell you why the 14 parameters of omega B97M-V were retained versus the remaining 130 that were thrown out. Some of my expectations were not fulfilled. I expected that smoothness would be critical, and that is partially true, but not fully true. We retained some quite nonlinear terms. I was surprised that happened. So I have a bit of difficulty, but again, the way I think about it is that actually we are on a very, very flat, dimpled, like, egg carton, gigantic dimensional egg carton surface where, there are tens of thousands of functionals that can perform almost as well as the one we chose to select. And so perhaps it's not too surprising that one has, some quirky features, so do most of the others. To be continued.
Thank you.
So this video is being recorded, so let me make a clarification. The right answer for the right reason is Ernest Davidson, not Fritz Schaefer.
Oh,
we had an MQM
It's been stated
for Ernie
twice,
on that motto.
Thank you.
So, what about the density itself? Are they much better? Because I can say that many molecular magnetic properties, they suffer because of a poor density, because of the diamagnetic part. And that's certainly determined by the density. And unless the densities get better, there's little need to work on other parts of it.
You're right, Trygve, as usual, and one of my other responses to the 2017 science paper was to begin a small benchmarking exercise on dipole moments and polarizability, since one is the lowest moment of the electron density and the other is its first response to an electric field. And the results were broadly okay. In other words, the omega B97M-V is not the best functional for dipole moments, to my knowledge. Others surpass it, including the less sophisticated omega B97X-V, but it worked quite well. And that was absolutely independent test data that we had never used to validate or train. So again, when one asks, what should the more diverse data include? Well, those things are simply energy differences. They are part of our more diverse data set now.
Okay. More comments or points for discussion? If not, then I think we will thank you once again.